Hi, and welcome back to the Drawing Board by Tau Beta Pi. This week, we're looking at what is an ODE and separable equations as we start our series on differential equations. For starters, what is an ODE and what does it stand for? Well, ODE stands for Ordinary Differential Equation. Now, what the heck makes it ordinary? What's so ordinary about these ordinary differential equations? Well, it turns out that the reason they are called ordinary differential equations is to distinguish them from PDEs, which includes partial derivatives. So really all that it means is that we're not doing anything too fancy with partial derivatives. Now, to make something an ordinary differential equation, there needs to be one independent variable like t or x, depending on how you're writing out your equation. The easiest way to identify an ordinary differential equation is to, of course, first make sure that there aren't any partial derivatives, and then also to make sure that you only have one independent variable. So for example, if you have an equation like this where you have y prime of t minus x prime of t plus x of t equals 0, this is an ODE because t is our only independent variable and we have these functions and their derivatives. It doesn't matter that we have more than one function. In this case, we have both y of t and x of t to worry about, but that doesn't stop it from being an ordinary differential equation. Another example would be something like if you have y double prime of t minus y prime of t. So far so good because we have only one independent variable. But if you have something like x of k, suddenly this isn't an ODE anymore because we have more than one independent variable. We have both t and k to worry about. So this is not an ODE. And then of course, anything containing a partial derivative is also not an ODE. So if you have, say, a partial derivative of y, anytime you see a term like this, automatically, this is not an ODE. Before we go too much further, there is one really important factor in ODEs that can make them really nice. That factor is that if you are given a solution, you can verify if that solution is correct or not. So let's say we have this ODE, and we are told that a possible solution for this is that y of x equals x squared. We can plug this in to this equation to figure out if this is an accurate solution or not. So for starters, we know we have this y prime term we have to worry about, so let's start by taking the derivative of this possible solution, which is just 2x. And then we can plug both of these in to this equation to verify if it does in fact equal 0. So we have 2x minus 5x squared is 0. Now this is an equation that you could potentially solve for the value of x, but since these terms do not cancel immediately to give you 0, we know that y equals x squared is not the solution for this ODE. The easiest types of ODEs to solve are separable equations. And the reason that these equations are so easy to solve compared to other differential equations is because all you really need to do to solve them is to integrate. A separable equation is anything that's in the form dy dt is equal to some function of t times some other function of y. And you can see why you'd be able to separate this, because you can multiply your dt across and divide your gy across so that you have 1 over g of y dy is equal to f of t dt. Now all you need to do is to integrate both sides, and you can solve for y. An important thing to remember with these equations is that plus c is very, very important. Now we'll go over a couple example problems, starting with this one, where dy dx is equal to quantity x plus 1 over y squared. It's pretty easy to check if this is a separable equation or not by checking if it's possible to multiply or divide across to get all of our y's on one side and all of our x's on the other. In this case, that's pretty easy. This becomes y squared dy is equal to quantity x plus 1 dx. So this is always the first step with any separable equation, is getting all of your y's to one side and all of your x's to the other. Once you have all of your y's and x's on their appropriate sides, it's time to integrate. So the integral of y squared is 1/3 y cubed plus, we'll call it c1 since we're on the first side of the equation. And over here we have 1/2 x squared plus x plus c2. One nice thing about differential equations and having these c values is because they're constants, we can just lump them together and define them as a different constant. So we can rewrite this as 1/3 y cubed equals 1/2 x squared plus x plus just regular c. Now it's time to isolate y. So we can start by saying that y cubed is equal to 3 times all of this stuff, which is 1/2 x squared plus x plus c. And then we have to take the cube root. So y equals the cube root of 3 times 1/2 x squared plus x plus c. In this particular problem, we were told that y of 1 is 1, so we can use that information to solve for the actual value of c. Continuing from the last page, we have this equation and y of 1 equals 1. So we know that 1 is going to be equal to the cube root of 3 times 1/2 times 1 squared plus 1 plus c. We can simplify this down a little bit, so we have the cube root of 3/2 plus 3 plus c. We can go ahead and cube both sides of this equation to get rid of the cube root. So we have 1 is equal to 3/2 plus 3 plus c. If you do the math, c comes out to be -7/2. You might be wondering, why didn't I distribute this 3 to our c? It's for the same reason that we were able to lump c1 and c2 together earlier. Because c is a constant, you can do anything to it and be okay. We're solving for something that's going to get plugged back in at this position, and we just need to make sure that as long as we write our final equation correctly with c plugged back in, we'll be okay. Now that we've solved for this value of c, we need to go ahead and write the final form of our equation. So we have y equals the cube root of 3/2 x squared plus 3x minus 7/2, all under that cube root. And this is our final equation for y. We will move on to our second example of a separable equation. Now, in this case, there are no y's on this side, which makes things easy because you can leave your dy alone and just bring the dx over. So we have 1/x squared dx. Now that step 1 is done and our y's and x's have been separated or isolated from each other, we'll go ahead and just take the integral of each side. Now, last time I went ahead and wrote out the c1 and c2 terms. This time, I'm not going to bother doing that and jump straight to just having a regular plus c as that lumped parameter. So the integral of 1/x squared is -1/x, and then don't forget plus c, very important. In this case, y is already isolated, which is nice, and we can go ahead and plug in our conditions of y of 1 being equal to 5. So we know that 5 is equal to -1/1 plus c. Then, pretty easy, just solve for the value of c. In this case, c is equal to 6. And we can write our final equation, which is y equals negative 1 over x plus 6. For example 3, we have this equation, which again we can see you can pretty easily separate your x terms and your y terms to get them all on one side. So we can divide both sides by our y squared to get our y's all on the same side. And now we are left with 10 over x squared plus 1 dx. Now that everything's separated, you know the drill, it's time to integrate. The integral of y to the negative 2, or 1 over y squared, is negative 1 over y. This side is a little bit more tricky, but if you remember your integrating rules, this is 10 times the arctangent of x. And don't forget, always important, plus c. We could isolate y at this point by obviously multiplying across by negative 1 and then inverting both sides of the equation. But if we look at the way this equation is laid out and our particular initial conditions, it seems easiest to just solve for c now and then isolate y. You can do it either way, it just depends on what the equation looks like and what you think is going to be easiest. So we'll start by plugging in y, which is 2. We have 10 times the arctangent of 0 plus c. The arctangent of 0 is 0, so c is negative 1/2. Now we can plug this back in for c and isolate y. So we have negative 1 over y equals 10 times the arctangent of x minus 1/2. Distribute our negative and invert, so we have y is equal to negative 1 over 10 times the arctangent of x minus 1/2. And that is our final equation for y. Now that we've solved a couple example problems, we have a pretty solid algorithm for solving these separable equations. Your first step being to put all of your y's on one side and all of your x's on the other side. Once you've done that, you can integrate and never forget your plus c. And then finally, you can either isolate y or solve for c in that order or in the opposite order, depending on what is going to be easiest with your particular equation. Remember that if you aren't given any value that would allow you to solve for c, that doesn't mean that c is automatically 0. You still have to write plus c and isolate y, leaving c as an unknown. And with that, you now know how to define an ODE and how to solve separable equations. This has been The Drawing Board by Tau Beta Pi. Thanks for watching.